Hey everyone, welcome back. Today we're going to decode something you've probably seen, but never fully understood. If you've ever downloaded an AI model locally, maybe through Ollama or some other tool, you've almost certainly come across names like this: Gemma 4, 26B, A4B, IT, Q4KM. That's a mouthful. And if you stared at it and thought, what does any of this actually mean? You're in exactly the right place. Because unpacking that one confusing label is going to lead us to one of the most important ideas in modern AI, mixture of experts. Let's decode that model name piece by piece. The first part, Gemma 4, is just the model family and version. The IT means it's an instruction-tuned model, trained to follow directions. The Q4KM refers to quantization. Basically, how aggressively the model has been compressed to fit in memory. But the part we really care about today is 26B. A4B. The 26B means the model has 26 billion total parameters. Those are the numbers inside the neural network that define what the model knows. And the A4B? That stands for active parameters. Only 4 billion of those 26 billion parameters are actually used for any given piece of text the model processes. So here's the mind-bending idea. You have a model with 26 billion parameters, but at any single moment, only 4 billion of them are doing actual work. The other 22 billion are just sitting there, waiting. That's not a bug. That's the whole point. This is what mixture of experts means. Instead of one giant brain that does everything, you have a team of specialized experts. And for each piece of text that comes in, only a few of the most relevant experts are called upon. The result? You get the knowledge of a 26 billion parameter model at the computational cost of a 4 billion parameter one. Now, to understand where this idea comes from, we need to go all the way back to 1991. The year that Nirvana released Nevermind, the internet was barely a thing, and a group of researchers were busy solving a very different kind of problem. The key players were Robert Jacobs, Michael Jordan, Stephen Nowlin, and Geoffrey Hinton. Yes, the Geoffrey Hinton who would later win a Nobel Prize. They were wrestling with a fundamental challenge in machine learning called catastrophic interference. When a single neural network tries to learn multiple different tasks, learning something new tends to destroy what it already knew. Their solution was elegant. Instead of one network that does everything, what if you built several smaller specialized networks and let each one focus on what it's best at? Their 1991 paper, published in the journal Neural Computation, introduced what they called adaptive mixtures of local experts. The architecture was straightforward. You have a set of expert networks. Each one is a small neural network that learns to handle a specific part of the problem. And alongside them you have a gating network, whose only job is to look at the incoming input and decide which expert should handle it. Think of it like a hospital emergency room. When a patient comes in, a triage nurse, that's the gating network, takes one look and routes them to the right specialist. The cardiologist doesn't see every patient. Neither does the orthopedic surgeon. Each one only sees the cases that match their expertise. The very first real-world test of this architecture was a vowel recognition task. The team gathered audio recordings from 6 Japanese speakers, 2 women and 4 men, each pronouncing 4 different vowel sounds. Because every person's voice is physically different, a single network struggled to generalize across all speakers. But when they trained a system with 6 expert networks, something remarkable happened. The gating network, entirely on its own, figured out that each expert should specialize in a different speaker. 5 of the 6 experts each took ownership of one speaker's voice. And for the one remaining speaker who was harder to categorize, the system blended the outputs of 3 different male voice experts together. No one programmed this behavior. The system discovered it by itself. Now, the original MOE had a serious limitation. All the experts still ran their computations every time, even the ones that weren't selected. So you weren't actually saving any computing power. The breakthrough that changed everything came in 2017, when a team at Google Brain led by Noam Shazir published a paper with a gloriously audacious title, Outrageously Large Neural Networks. Their key innovation was sparse gating. The idea that you can have thousands of experts, but only activate a tiny handful of them for each input token. This is where the real efficiency comes from. The model's total knowledge, stored across all those expert networks, can be enormous. But the actual computation for any single token stays small and fast. The mechanism they used is called top K routing. For each word or token that the model processes, a gating network scores all the available experts and picks only the top 1 or 2. The rest are completely ignored for that particular token. No computation, no memory access, nothing. To give you a sense of the scale, in their original paper, they tested models with over 1,000 expert networks. But for any given word, only 1 or 2 experts would activate. That means you could have a model with 200 billion parameters, but the actual compute budget for each token looks more like a 12 billion parameter model. But there was a catch. When you let a gating network freely choose which experts to use, it tends to develop a very strong preference for just a few of them. Maybe 2 or 3 experts get picked constantly, because early in training they happen to perform slightly better. The others stop getting trained. They become useless. This problem is called expert collapse, and it's one of the central technical challenges of building MoE systems. The solution Shazir's team introduced was an auxiliary loss, a penalty term added to the training objective that forces the model to spread tokens more evenly across all experts. It's like a rule that says every expert on the team must get a fair share of work, or the whole team gets penalized. The sparse gating paper opened the floodgates. In 2020, Google released G-Shard, a 600 billion parameter multilingual translation model using MoE, distributed across 2,048 experts. Then in 2021 came the switch transformer, which pushed things to 1.6 trillion parameters. The switch transformer made a surprising discovery. You don't even need TOP2 routing. TOP1, just picking the single best expert for each token, was simpler, cheaper to communicate across hardware, and trained 4 times faster without sacrificing quality. Also in 2021, Google's GLAM model demonstrated something crucial. A 1.2 trillion parameter MoE model could outperform GPT-3 while using only about 1/3 of the energy during inference. Bigger model, less electricity. That combination would prove irresistible. For years, MoE was mostly locked inside big tech research labs. That changed in December 2023, when a French startup called Mistral AI released Mistral 8x7b to the public. The name tells the story. 8 expert networks, each with 7 billion parameters. The total parameter count is about 46 billion, but during inference, only about 12 billion activate at any time. The results were stunning. Mistral matched or outperformed GPT 3.5 on many benchmarks, while being fast enough to run on consumer hardware with a good GPU. It was the moment MoE went from a research curiosity to something anyone could download and run at home. Then came DeepSeek v3 in late 2024, and it represented a genuine leap forward in MoE design. The team introduced 3 innovations that are now being copied across the industry. First, shared experts. Instead of routing all tokens through competition, certain expert networks are always active for every token. These shared experts learn universal language patterns, grammar, basic facts, reasoning structures, while the routed experts specialize deeply in narrow domains. Second, fine-grained experts. Rather than a small number of large experts, DeepSeek used a much larger number of smaller, more specialized ones. Third, and most elegantly, they solved the load balancing problem without any auxiliary loss at all. Instead of penalizing imbalance through a loss function, which slightly hurts model quality, they added a dynamic bias term to each expert's routing score that automatically steers traffic toward underloaded experts. The training objective stays clean, and the balancing happens as a side effect. DeepSeek also tackled a different bottleneck that MoE models face during inference. As these models generate text, they need to cache enormous amounts of intermediate data, called the KV cache. For a model with hundreds of billions of parameters, this cache can easily overflow GPU memory. Their solution, called multi-head latent attention, compresses this information into a much lower dimensional space before storing it, and then expands it back out when needed. The result was up to a 28 times reduction in memory usage for this part of the computation, a huge practical win for anyone trying to serve these models at scale. The trend in 2025 and 2026 is moving toward what researchers call fine-grained MoE. Instead of 8 experts or 64, newer models are using hundreds or even thousands of tiny expert networks, each extremely narrow in focus. Take the Qwen 3 family as an example. A model like Qwen 3 to 35 BA3B has 35 billion total parameters, but only 3 billion active at once. That's an activation ratio of less than 10%. As compute budgets increase, it turns out that adding more, smaller experts consistently outperforms adding fewer, larger ones. You get richer specialization with less computational overhead per token. One more evolution worth understanding is how the routing itself has changed. The original approach, which researchers call token choice routing, lets each token vote for which expert it wants to go to. It's intuitive, but it creates traffic jams. Popular experts get flooded while others sit idle. In 2022, Google proposed flipping this around with expert choice routing. Instead of tokens choosing experts, each expert selects its favorite tokens from the incoming batch. This design guarantees perfect load balance by construction. No auxiliary loss needed, no overflow. And it has a nice bonus. Genuinely hard or complex tokens can attract attention from multiple experts simultaneously, giving them more processing power where it's needed most. So let's bring it all the way back to where we started. When you see Gemma 4, 26B, A4B, you're reading a summary of everything we've talked about. That model contains the accumulated knowledge of 26 billion parameters, organized across a team of specialized expert networks. But when it reads your question and starts forming a response, only 4 billion parameters are active at any given moment, the ones whose expertise is most relevant. That's the mixture of experts architecture in action, efficiency and capability, not as a trade-off, but working together. That's the magic of MoE, and it's the reason why almost every serious large language model being built today uses some version of it. That's it for today. See you in the next one.